The Royal Swedish Academy of Sciences has decided to award the Nobel Prize in Physics 2021 for groundbreaking contributions to our understanding of complex physical systems, with one half jointly to Syukuro Manabe, professor, senior meteorologist at Princeton University, USA, Klaus Hasselmann, Professor Max Planck Institute for Meteorology, Hamburg, Germany, for the physical modeling of Earth's climate, quantifying variability and reliably predicting global warming. And the other half to Giorgio Parisi, professor at Sapienza University of Rome, Italy, for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales. Now, what is climate modeling? A climate model is a computer simulation of the Earth's climate system, including the atmosphere, ocean, land, and ice. They can be used to recreate the past climate or predict the future climate. Building and running a climate model is a complex process of identifying and quantifying Earth system processes, representing them with mathematical equations. Let us see an UCAR simulation demonstrating Earth's energy balance with simplest mathematics but giving a nice idea to school level students for climate modeling. Here it is assumed for simplicity of math. The model has one extreme simplification. It assumes Earth has no atmosphere. That makes for simple math, but it is clearly unrealistic. Earth's atmosphere acts as a blanket, making our planet habitable. Without the heat-trapping greenhouse gases in our atmosphere, Earth would be a frozen ball of ice. Let us see. If the temperature of the Earth's surface is given by this equation, and if there is no atmosphere, then what is the temperature of the Earth's surface? Albedo is the percentage of reflection, reflectivity. Average reflectivity or albedo of Earth's surface is 31%. So at this 31% albedo in this formula, it gives 253 Kelvin, that is minus 20 degrees centigrade. Let us choose sea ice. Its albedo is higher, reflectivity is higher, 45%. Yet the temperature is 239 Kelvin, that is minus 34 degrees centigrade. That is, temperature of the surface of the Earth is minus 34 degrees centigrade. That is, Earth would be a frozen ball of ice if there is no atmosphere. Slide is for those who are interested in the derivation of the formula used in the previous slide. This is Giorgio model. In this model, the canonical Klaus of energy balance model, it is assumed that the globally average sense we can write if T be the temperature of the surface of the Earth, then rate of change of surface temperature dq being Cp dt, where Cp is the effective heat capacity, then rate of change of surface temperature is given by amount of energy absorbed per second by the Earth, where alpha is equal to albedo, that is reflectivity. So 1 minus alpha is absorptivity, that is rate of amount of energy absorbed by the earth, S0 being the incident energy. So S0 into 1 minus alpha is the amount of energy absorbed per second, and amount of energy radiated, sigma T to the power 4T, is the absolute temperature of the surface of the earth, and epsilon being the emissivity. So this is the net amount of energy radiated per second. So it is Cp delta delta. So at the steady state, when temperature is constant, then this is equal to 0, yielding this equation. This temperature is called bare point temperature because in this calculation, in this model, the atmosphere is neglected. That is, effectively in this calculation does not include the infrared contribution of the atmosphere and hence does not deal with the greenhouse effect. As it is discussed in the previous simulation, it is a simplified model. In consequence, this is often referred as bare planet temperature, and it is cold and naturally minus 15 degrees centigrade or minus 20 degrees centigrade as already shown in previous simulation. But with the help of this model, we can proceed if they are not equal. If this two amount is not equal, then this is not equal to 0. Then it will increase the surface temperature of the earth. And this is the basic idea of computer simulation or climate model in this way. 100 years ago, Fourier first understood the atmosphere's role in radiation balance between the shortwave solar radiation coming towards our planet and the Earth's outgoing longer wave infrared radiation which is absorbed by the atmosphere, thus heating it. Ecolan, the colleague of Arrhenius, called this as greenhouse effect. Arrhenius, at the end of 19th century, proposed that outgoing radiation is proportional to the radiant body's temperature to the power 4. Hotter surface of temperature of the sun is 6000 degrees centigrade. The source of radiation shorter is the emitted wavelength. Earth's surface temperature, say 15 degrees centigrade, emits longer wavelength invisible infrared radiation. Earth re-radiates infrared radiation. If the atmosphere did not absorb this radiation, the surface temperature would be barely exceed minus 18 degrees centigrade, as just shown in the previous slides. Arrhenius arrived at the conclusion that if the level of carbon dioxide in the atmosphere halved, Earth will enter a new ice age. A doubling of carbon dioxide would increase the temperature by 5 to 6 degrees centigrade. But this calculation was not accurate in our perspective, but at that time it was very nice prediction. But weather and climate are more complex. Manabe developed a physical model of Earth's climate exploring interaction between radiation balance and the vertical transport of air masses, as well as the latent heat of vaporization. Most powerful greenhouse gas is water vapor, but we cannot control the concentration of water vapor in the atmosphere. But as carbon dioxide level increases in the atmosphere, making it warmer, allowing more water vapor to be held in the atmosphere, which increases greenhouse effect and makes temperature rise even further. If carbon dioxide level drops, some of water vapor will condense and temperature will fall. This is the basic idea of the Manabe's climate model. Increased levels of carbon dioxide lead to higher temperatures in the lower atmosphere while the upper atmosphere gets colder. Manabe thus confirmed that the variation in the temperature is due to increased levels of carbon dioxide. If it was caused by increased solar radiation, the entire atmosphere should have warmed up. This graph clearly shows this. Moreover, note that blue line is for 150 ppm carbon dioxide, black line indicates 300 ppm carbon dioxide and the red line is for 600 ppm carbon dioxide. That is, if the amount of carbon dioxide is doubled with respect to black line, the temperature increases. Whereas if it is halved, indicated by blue line, the temperature decreases. The temperature at the surface fell by 2.28 degrees centigrade when the level of carbon dioxide halved. It increased by 2.36 degrees centigrade when the level of carbon dioxide doubled. Arrhenius model thus achieved the correct shape. Result is now more deterministic. The work of Manabe just described was published in 1960. After almost 10 years of Manabe, Hasselmann linked seemingly chaotic weather and climate. Weather is so chaotic that an example is sufficient for that. Uniform heating by just 1 degree can take thousands of years for ocean, but few weeks for atmosphere. The decisive trick was incorporating rapid changes in weather into the calculations as noise and showing how this noise affects the climate. Hasselmann created a stochastic climate model, which means that chance is inbuilt into the model, like random walk model. Using this theory, Hasselmann demonstrated the rapidly changing atmosphere can actually cause slow variation in ocean. Hasselmann's work provides the framework from purely spatial data to spatiotemporal data. Instead of looking into for a needle in a tiny corner of a haystack, then the next tiny corner of the haystack, Hasselmann advocated for the most important strategy, searching the whole haystack simultaneously. He also pointed out the theory, observation, and models provide considerable information about signal and noise properties. Namely, the detecting of a signal may not necessarily associated with parts of data where signal is strongest, but rather where the noise is weakest, thereby revealing a more nuanced physical interpretation of components of the system. Once the model for climate variation was finished, Hasselmann developed methods for identifying human impact on the climate system. He sorted changes in solar radiation, volcanic particles, or levels of greenhouse gases, leave unique signals, fingerprints, which can be separated out. These methods for identifying fingerprints can also be applied to the effect that humans have on the climate. Look at this graph. This is the most identifying fingerprints in the climate. Hasselmann developed methods for distinguishing between natural and human causes called fingerprints of atmospheric heating. Comparison between changes in the mean temperature in relation to average 1901 to 1950, 1900 to 2000, this is the plot, and in y-axis observations of changes in temperature. Look at the blue line. Blue line is the calculation that show the effect of only natural sources such as volcanic eruption. Thus, the effect of gases from volcanic eruptions is not so drastic, not so important. It is almost constant. But the calculations of the effect of both natural and human sources, the red line, it is very high. The temperature rise is very high. And observation is just like the black line is the observation, which is which supports which supports the calculations of the effect of both natural and human sources. That is, blue line is due to natural sources like gases from volcanic eruptions, and look, its effect is not so dominant. Red line shows calculation based on temperature rises more due to the human activities or human intervention. And the actual observation is supports the calculation of the effect of both natural and human sources. So this is the clear fingerprint that human intervention or human activities definitely increases the temperature. Geometrical frustration is an important feature in magnetism, where it seems from the relative arrangement of spins. A simple 2D example is shown in the figure. Three magnetic ions reside on the corners of a triangle with antiferromagnetic interactions between them. The energy is minimized when each spin is aligned opposite to neighbors. Once the first two spins are aligned antiparallel, the third one is frustrated because its two possible orientations up or down give the same energy. The third spin cannot simultaneously minimize its interactions with both of the other two. Since this effect occurs for each spin, the ground state is six-fold degenerate. Only the two states where all spins are up or down have more energy. A spin glass is a metal alloy where iron atoms, for example, are randomly mixed into a grid of copper atoms. Each iron atom behaves like a small magnet or spin, which is affected by the other magnets around it. However, in a spin glass, they are frustrated and have difficulty choosing which direction to point. In the introduction to his book about spin glass, Parisi writes that studying spin glass is like watching the human tragedies of Shakespeare's plays. If you want to make friends with two people at the same time, but they hate each other, and it can be frustrating. This is even more the case in a classical tragedy, where strongly emotional friends and enemies meet on stage. How can the tension in the room be minimized? Spin glasses and their exotic properties provide a model for complex systems. In the 1970s, many physicists, including several Nobel laureates, searched for a way to describe the mysteries and mysterious and frustrating spin glasses. One method they used was the replica trick, a mathematical technique in which many copies, replicas of the system, are processed at the same time. However, in terms of physics, the results of the original calculations were unfeasible. In 1979, Parisi made a decisive breakthrough when he demonstrated how the replica trick could be ingeniously used to solve a spin glass problem. He discovered a hidden structure in the replicas and found a way to describe it mathematically. It took many years for Parisi's solution to be proven mathematically correct. Since then, his method has been used in many disordered systems and become a cornerstone of the theory of complex systems. Both spin glass and granular materials are examples of frustrated systems in which various constituents must arrange themselves in a manner that is a compromise between counteracting forces. The question is how they behave and what the results are. Parisi is a master at answering these questions for many different materials and phenomena. His fundamental discoveries about the structure of spin glasses were so deep that they not only influenced physics but also mathematics, biology, neuroscience, and machine learning because all these fields include problems that are directly related to frustration. Parisi has also studied many other phenomena in which random processes play decisive role in how structures are created and how they develop, and dealt with questions such as why do we have periodically recurring ice ages? Is there a more general mathematical description of chaos and turbulent systems? Or how do patterns arise in a murmuration of a thousands of starlings? These questions may seem far removed from the spin glass. However, Parisi has said that most of his research has dealt with how simple behaviors give rise to complex collective behaviors, and these applies to both spin glasses and starlings.